I'm recording now. If it freezes, Blackboard Collaborate, say something in your mic or use the hand raise feature. All right, so here, what we're going to learn about in this section, which is actually section 1.1, what we're going to learn about here is equations. Now, before we actually get to equations, we actually have to look at vocabulary with equations. I know vocabulary might not be something you expect to see in a math class, but math does have a lot of precise, academic language, academic vocabulary with it. Okay? So we're going to look at that first. Then we're going to look at how to solve equations in general, and we're going to focus on linear equations in this section. I mean, what's nice about them, as you'll see, is they're pretty easy to solve. When we get to the next section, it'll take a little more work because we're going to have to deal with quadratic equations. All right, so for now, let's focus on equations and linear equations. All right, so let's get to the vocabulary. Okay, so in algebra, what you're going to deal with are terms. We have seen these before. And again, a term is nothing more than a number, a constant, or a variable. Or you could take a product of these things. I mean, for instance, we have seen them, like 5x, x alone, 12. Those are terms. When we looked at polynomials, we saw terms as well. The terms made up a polynomial. I think we called the terms as well. Okay? All right, now, from terms, we can form what are called algebraic expressions. Or, they're just simply called expressions here. But basically, an algebraic expression is a meaningful combination of terms using the operations of arithmetic. In other words, when we combine them, we use the operations like addition, subtraction, multiplication, division, that kind of thing. Here are just some examples. A term alone, wait, let me get that. A single term alone is actually an expression. But here are some others. You can add or subtract them, you can form expressions pretty easily. So we start out with terms, we go to expressions, then we go to equations. An equation is when you have one expression equal to another. Well, excuse me, let me restate that. It's a statement that one equation equals another. An equation in one variable, that's when at least one of the equations has the one variable. And there's only one variable, so you're not going to have something like this, 2xy plus 1. And you're not going to have x on one side and y on the other. You can only have one variable. Okay. Also, since it is a statement that the two expressions are equal, it could be false equation. You could have an equation that's never true. For instance, you could have something like this. That's an equation. However, it's false. We know that 1 is not equal to 2. Okay? We know 1 is not equal to 2. So we have an equation here that's false no matter what. Now, okay, so that's an equation. Now, there's also this concept of the domain, namely the domain of the variable. That's just a collection of all numbers for which both sides of the equation are defined. I know I have the word set here. The book does a lot of set theory, but I'm not going to do, I don't really want to do set theory in this course. Not to say you can't handle it. It's just for the purposes of this course, I really don't think it's appropriate, set theory. But when you see the word set, you could just think, oh, a collection of, or a group of if you want. So that's what the domain of the variable is. Again, it's the collection of or set of, so collection of all numbers for which both sides of the equation are defined. Here's an example. 19, no matter what x is, 19 is defined, right? 19 is a number. 7x plus 1, well, you can replace x with any number on the planet, right? 1, 2, 0.8, negative 6 trillion, whatever number you want, 7x plus 1 will be defined. So in other words, both sides here are defined for all real numbers. Hence, the domain variable is all real numbers. So that's what happens here. But you could have an equation where that's not the case. That is, the domain does not contain everything. For instance, let's look at this equation. I mean, here, there's no restriction on 2. 2, you could take x to be anything, and 2 won't change. But the right-hand side, well, that's a different story. As you can see, right, you can see here, the denominator is not going to make sense if x is 1, right? If you replace x by 1, we get 5 over 0. That's a no-no in mathematics, right? You never divide by 0. Hence, the right side is not, it's only defined for x not equal to 1. So because, and the left side's defined no matter what. So the domain of this variable, so the domain here, in other words, is all x except 1, or all numbers except 1. If you write in words this, something like this, then that'll be full credit. In the book, they'll probably use fancy set notation to state the domain. But again, I'm not going to use fancy set notation. So if I aim for the domain, you could just write it out in words. You can write all numbers except 1. So hopefully that makes sense what I'm trying to say. Okay, that's one example. What about this one? Well, we saw in section P6, right, the previous one with square roots, that the square root is only defined if you're for 0 or positive numbers. In other words, you can only take the square root of a non-negative number. You can only do that. You can take the square root of a non-negative number. So x here is only going to exist for x that's either 0 or positive. In other words, the right-hand side is only defined for non-negative x. The left side here, x plus 1, there's no restriction there. You could take any number out there and add 1 to it, right? Nothing wrong with that. So altogether, the domain is all x such that x is non-negative. Or again, all numbers that are greater than or equal to 0. We haven't done this notation yet, but this notation just means all x greater than or equal to 0. It's just notation for saying x is non-negative. So that's a domain here. Okay, and it will come up again. All right. Now, let's consider this equation. Also, again, I did email you the notes, so, you should have them. I will put the full notes on Blackboard once I'm able to, hopefully this weekend. So let's look at this equation. 2x plus 1 equals 2. I mean, it should be easy to see that the domain is everything, right? The right-hand side is defined no matter what x is. The left side here, 2x plus 1, right? That's defined for every x, no matter what x is, okay? No matter what x is, right, 2x plus 1 is going to make sense. So the domain is all real numbers. But let's have some fun. Let's actually replace x with explicit numbers. So for instance, what happens if x is 1? Remember, an equation could be true or false, right? So if x is 1, the left side becomes 2 times 1 plus 1, which we know is 3. And so this equation becomes 3 equals 2. Well, that's a false, isn't it? 3 is not equal to 2, so that's false. Okay, that's okay. What about if x is 0, excuse me? Well, in that case, the left-hand side becomes 2 times 0 plus 1, right? But that's just 1. 2 times 0, that's 0. 0 plus 1 is 1. So in this case, the equation will be 1 equals 2, because again, the left side will be 1. But this is also false. Now, we could keep doing this for as many integers or any numbers as we want. But watch what happens if I replace x with this number, a half. Well, then the left side, right, by direct calculation, 2 times half is 1. So 2 times a half plus 1, well, that's just 1 plus 1, which is 2. So because of that, this equation becomes 2 equals 2. But is that false? No, that's a true statement. So in other words, this x, when plugged in for x here, this number let me say it again, this number when plugged in for x gave us a true statement. So because of that, we say this number is a solution to the equation. In other words, any value of the variable that makes the equation true, when you plug that number in for the variable, is called the solution of the equation, or a root. So that 1/2 we just found is a solution to that equation. Okay, so that's what a solution is to an equation. And of course, with these equations, we like to find the solutions. And that process is called solving the equation. So when you actually go about solving the equation, that process is finding all the solutions. All right, okay. Also, this comes up more in the book. I don't think Lumen Learning does this, but there's this notion of the solution set. That's just the set of all solutions. That's all it is. Or so if you want, it's the collection of all solutions to an equation. If there are no solutions, then the set is empty. So it does make sense to consider the empty set. That's just a set of nothing in it, the set with nothing in it. So just something I wanted to point out. All right, let me get the recording. Let me just stop the recording.